This is the virtual lecture for March 18th, looking at some of the aspects of rotational dynamics. So let's get into that. First definition we need is the definition of the influence that a force has when an object has an extended structure. Remember, up till now all of our objects have been treated as point objects with no extension, so there's no opportunity for rotation to occur because the point object merely experiences a point force and moves in the direction of that force and accelerates and so on. Now that we've extended our objects to real objects that have length, width, and height, forces can be applied that will create rotational influences. The diagram shows a force F here. Oops, why did you do that? Okay. Alright, let's get a pen here. Color. Good. Force F here applied to this triangular wedge-shaped object that is going to pivot around the base here. So essentially the object will be tilting in response to that applied force. So in determining the motion of the object, we can't use the same Newtonian equations we had before because we're not talking about linear motion. Now we're talking about rotational motion. So we know that to describe rotation, we already realize that we're going to have to use theta as our angle, right? So if we kind of think back, well, previously we had F equals ma. Okay. In our rotational kinematics conversion, we knew that we replaced the acceleration a with alpha, and we need to determine, well, what are we going to replace the influence with, F here, in this equation, so we can write an equation that applies to rotational motion. That's going to be the torque. You see that's defined over here as the product of the force times the lever arm times the angle, sine of the angle between the direction of the force. The force is going that way and the lever arm is going, whoops, that way. So there's a 90-degree angle there between those two directions. So that's what the sine of 90 will be, equal to 1 in that case. Those forces don't have to be 90-degree angle, they can be at any particular angle. But in this case, when you have a 90-degree angle, you get the maximum amount of torque. And the units on torque are the units, of course, that are on the equation. So you see you have a unit of force, the Newton, and a unit of distance, the meter. So the Newton meter will be our unit of torque. So that's what we're going to replace in F equals ma with the influence. We're going to replace the force with the symbol tau, which stands for torque. So we have an equation, tau equals something times alpha. The something is, how do we describe the mass when dealing with an extended object? Because now the shape matters. So it's not just the quantity of material there, it's what the material looks like, how it's extended in 3 dimensions or 2 dimensions. So that's something we're going to need to talk about a little bit further. But we just want to get the definition of torque down first before we go into that. Okay, let's move ahead. Now, I'm stating here the final form of Newton's second law for rotation. Torque equals capital I, moment of inertia, which I want to talk about briefly, times the angular acceleration. So you can kind of see that the way we developed the equations for rotational kinematics, we replaced x with theta and v with omega and a with alpha. So we want to continue that substitution when we get to the dynamics equations and realize that we have to replace, to convert our dynamics equations from linear forms to rotational forms. We now can see that we're going to replace the force wherever we see force with tau. We're going to replace the mass wherever we see that with this symbol I, which stands for moment of inertia. And we're going to replace the symbol P for linear momentum with angular momentum L. So for example, the work equation that we had, work in linear motion was force times distance, right? Fx cosine theta, but let's just drop the cosine theta for now and have the force and the distance x in the same direction, so we don't have a cosine theta term. If we convert that to rotational work, then the force is replaced by tau, and the linear displacement is replaced by the angular displacement theta. And so there's your work expression for rotational motion. Work equals tau theta. All of the forms of the equation stay the same. We're just changing the symbols. So for instance, kinetic energy, 1/2 m omega squared, 1/2 mv squared. Oops. We want to keep the same form, so for rotational motion this will become 1/2. Anyway, we're having m, we replace that with I, and we replace v with omega. So 1/2 I omega squared is rotational kinetic energy. Okay, well, you can find these formulas in Chapter 8. Let's jump ahead and take a look at this idea of moment of inertia. Alright, here's a definition for objects that can be considered point objects. In other words, if you can idealize an object to just points of a structure connected by thin massless rods. Okay, so the rod in here doesn't really count. What we're just talking about in this particular case is we have a mass here and we have a mass here. Okay, so that would be a structure. And in this case it's rotating about one end, but we could have the axis of rotation anywhere along here. We could have the axis of rotation in the middle, or the axis of rotation could be at some angle. It doesn't really matter, but wherever the axis of rotation is, it's going to change the moment of inertia, because what the moment of inertia is telling us is how difficult is it to rotate this object. Notice the word inertia. Remember, inertia really refers to, in linear motion, inertia is measured by expressing the mass, and inertia is resistance to being accelerated. Okay, so, and that's Newton's second law, isn't it? The mass m is in F equals ma, has a proportionality factor that says this is how difficult it is to accelerate this object. M times the acceleration is the necessary force. In the case of rotation, we want to twist the object. Okay, so the resistance to being twisted is encompassed in this term, moment of inertia. And it's not just one number, because the resistance will change depending on where the axis is rotated relative to the location of the masses in the structure. So notice this particular summation. The m's here says m sub I, so that's mass 1 or mass 2 or mass 3, however many you have. And r sub I is the location of each mass relative to the axis of rotation. So for instance, on this picture here, if this is m1, right, and this is m2, then m1 would have a value of r1 equal to 0, because it's on the axis of rotation. Whereas the value of r for m2, maybe we'll just call it L, right? Just call it, ooh, that's a bad L. L, so that's the distance from the axis of rotation to the point where the mass m2 is located. If we change our axis of rotation to say here in the middle, then m1 would be at L over 2, and m2 would be at L over 2. Oops. And we'd get a different calculation for this summation, m1 r1 squared plus m2 r2 squared. So the moment of inertia is not one single value for a structure. It's an infinite number of values depending upon the location of the axis of rotation. Now, most objects are not point objects, are they? Real objects have extension and made up of billions and trillions of atoms. So we have to treat a real object as a continuum. And when we do that, this particular relationship here becomes, let's see if I can write this, an integral, where that capital sigma there stands for sum, doesn't it? Becomes an integral in calculus of r squared delta m. And what that really is just saying, break up the object into tiny, tiny pieces, and relative to the axis of rotation, go out to a small, tiny chunk and square the distance times that little tiny mass, and sum it up for the whole shape of the object. Fortunately, we don't have to do that. With the objects we're dealing with, we have a table right down here where it's all been done for these basic shaped objects. So you can see that for a sphere, which is rotating about its center, okay, this is a solid sphere, not a hollow sphere. Its moment of inertia is 2/5 mr squared. Mass of the sphere and the radius. If the sphere were hollow, this would actually be 2/3 mr squared. Now that's down here, thin spherical shell. Okay. At any rate, those are well-known formulas, so we can use those as we need to. Down here is a relationship ml squared over 3 that you have used or are going to use when you do the online lab for this week, because the one vane in a 3-rotor blade will have a moment of inertia relative to one end. The end that's attached to the hub will be ml squared over 3. Okay, so the moment of inertia is something that expresses for us the difficulty in this object being rotated. Okay? So here's kind of a compilation of the formulas that deal with rotational dynamics that are in Chapter 8, showing you calculation of the kinetic energy of rotation, work, the angular momentum, and the relationship between force and acceleration. Also how angular momentum is related to torque, and the power equations. Okay. conservation of energy as well as conservation of momentum still apply regardless of the type of motion we're dealing with. So here, for example, is the extended equation for conservation of energy that includes our usual term for linear kinetic energy and the potential energy, whatever that would be that you're dealing with, whether it's gravity, it would be mgh, or whether it would be a spring, 1/2 kx squared. But the new term in here is the energy associated with the rotational motion, rotational kinetic energy, 1/2 I omega squared. You can call that k sub r if you want. Okay, so let's apply these ideas to a couple of problems from your homework set. So you've got a mass, and you've got an inclined plane that's a certain height, y. And we're told it's a solid disk, so that's going to allow you to determine what is the moment of inertia. Go to the table and look it up. And we want to know what's the kinetic energy of the disk at the bottom of the plane, first of all, and here's the radius. Okay. So it doesn't specify which kinetic energy, so it's just the total kinetic energy at the bottom of the plane, which will be the sum of the rotational and translational kinetic energy. So I would use conservation of energy to determine what that is, because at the top it's all potential energy, at the bottom it's all kinetic energy, and there's no friction here. Okay, now at the bottom we want to know how fast is it moving, so we're looking for V, aren't we? Okay. Now at the bottom, if all of the energy is kinetic energy, and that must be equal to the potential energy you had at the top. In other words, potential energy U0 at the top equals the total kinetic energy at the bottom, which is comprised of translational kinetic energy plus rotational kinetic energy. Okay. Oops. And you'll know a number for U, because it's just mgy, isn't it? And then down here at the bottom you've got 1/2 mv squared and 1/2 I omega squared. And what else do we know about rolling without slipping? Don't we also know the fact that rolling without slipping means V is related to the rotational velocity through omega r. So we can eliminate omega in favor of V and calculate how fast it's going at the bottom. Okay. Alright, that's it for that. We'll see you on Thursday.